Listen up, grab your notebook, kid. We're skipping all the fluff today and hitting the hangar floor to prep for your B1 EWIS certification. This explainer right here, this is your EASA M7.7 EWIS B1 test prep. I'm going to walk you through exactly what you need to know to pass the exam, but more importantly, I'm going to tell you why we actually do it this way out on the line. Let's get straight to work. Section 1, cable specs and routing. Let's get into it. Okay, look at these essential rules. When you're pulling a wire, you absolutely must identify it by its specific wire number and its gauge. And they're stamped right on the jacket. Remember, that gauge size is identified by the AWG standard. That's American wire gauge. Now, here's a crucial one. Any conduit you use must have an inner diameter that is exactly 25% larger than your cable bundle's maximum outer diameter. Why do we do that? Well, it's not just to make your life easier when pulling it through. That extra space is mandatory to allow for heat dissipation, and it prevents the cables from binding up and stressing during the installation. Now, routing separation. You have to respect these clearances like your life depends on it, because honestly, it does. Keep your electrical cables at least 3 inches away from any control cables. If a wire bundle sags and snags a flight control cable, you've got a massive problem on your hands. But even more critical, your wiring must maintain a minimum of 6 inches of separation from fuel or oxygen lines. Think about it. A chafed wire sparking right next to a highly flammable leak? That means a catastrophic fire. 6 inches, memorize it. Next up, you're going to see a lot of shielded wire inside modern avionics base. We use shielded wire for a very specific reason, to keep our signals clean. It allows the transmission of electricity without blasting out EMI, electromagnetic interference, or HIRF, high-intensity radiated fields. Without that shielding, the electrical noise from one system could completely blind the navigation or communication avionics sitting right next to it. Section 2, clamps, crimps, and soldering. Let's take a look. You are absolutely going to be tested on clamp applications. Plastic clamps, they stay strictly inside the pressure cabin, where the environment is perfectly controlled. But when you are out in the wheel wells or unpressurized zones using metal cable clamps, they must have a flexible rubber cushion. And the reason is simple. That rubber cushion absorbs the constant vibration of the airframe. Without it, that bare metal clamp will act just like a tiny saw blade, slicing right through the wire insulation over time. You also really need to know your hardware limitations. Don't go throwing plastic tie wraps into the engine blocks or near bleed air ducts. They are only permitted in areas where temperatures do not exceed 120 degrees Celsius. Any harder, and they'll literally just melt away. Oh, and those unbonded clams you see kicking around in the bins? Those are strictly for securing wiring only. Never, ever use an unbonded clamp to secure a metal hydraulic, fuel, or oil line. Now, when you're terminating a thick gauge wire, you'll be reaching for a hydraulic crimping tool. First step, clear all the debris out of your crimp dies. You have to ensure they are completely clean before you even try to gauge them with your go-no-go tools. If there is grit in there, your gauge reading is basically a lie. Second, when you make the actual crimp, always operate that pump several times. You've got to ensure the crimping operation is fully completed and locked in tight, because a weak crimp means high resistance, and in this business, high resistance means heat. Listen, if you have to solder a connection, don't just melt metal and pray it holds. You must apply flux first. Flux does 3 critical things for us. It cleans the surface, it acts as a shield to block oxygen from ruining the joint, and it actually aids the soldering process itself. Also, check your materials. Ensure your solder contains cadmium. Why cadmium? Because it drastically lowers the melting point of the solder. That means you get a rock-solid joint without having to apply so much heat that you fry the adjacent circuit boards. Section 3, testing and electrical bonding. Let's get the definition totally straight here. Bonding isn't just about mechanically tying things together with a strap. Bonding is the purposeful, electrical interconnection of the airframe's metallic parts. We do this to safely bleed off the static charges that build up during flight and, crucially, to provide a safe, massive conductive path for lightning strikes. We want that energy to flow through the skin, not blow a hole in a fuel tank. The exam is definitely going to ask you about testing these bonds. When you hook up your bonding tester, just know that it normally tests at a magnitude of 10 amps to ensure the path can handle a real load. And if you're out there checking a Class A bonding installation, like an antenna for instance, your resistance absolutely cannot exceed 2.5 milliohms. Seriously, anything higher than that, and your antenna just becomes a lightning rod with nowhere for that massive energy to safely go. So to check the health of the wire's jacket to verify there's no hidden insulation breakdown, you're going to grab a Megger insulation tester. A megger generates a massive 500 volts or more. The fundamental rule you need to remember here is that your test output voltage must always be equal to or preferably higher than the actual working voltage of the circuit you're testing. You have to stress that insulation past its normal day-to-day load to prove it's actually safe to fly.
All right, kid, here's a floor scenario for you, something you are definitely going to see on the B1 test. What do you think happens if the impedance on your coax cable installation doesn't perfectly match the load impedance all the way at the other end?
Well, it's simple physics, but trust me, it's bad news. Not all the energy you're feeding down the line actually flows into the load. Because of that mismatch, the energy hits a wall and reflects right back toward the source, forming what we call standing waves. And when standing waves occur, your avionics are essentially starving. They aren't getting the signal power they need to operate correctly. So, how exactly do we diagnose that mess? To catch those standing waves on a coax line, you're going to use a time domain meter to measure the VSWR. That stands for voltage standing wave ratio. And if you need to find exactly where that cable is broken or pinched, you rely on a TDR, a time domain reflectometer. The TDR sends a pulse down the line, measures the reflected power, and then calculates the exact length of the cable right down to the millimeter where the fault is hiding. It is an absolute lifesaver for troubleshooting.
And finally, Section 4, Inspections and EWIS Hazards.
First up, a hard legal rule. A general visual inspection of an aircraft structure may be accomplished by the maintenance crew only, period. Don't ever let a pilot or a ramp agent tell you they've looked it over and it's fine. That sign-off is the sole legal responsibility of certified maintenance personnel. Now, out in the hangar, your absolute bread and butter is the zonal inspection. This is a general visual inspection of a specified area or zone to detect obvious unsatisfactory conditions and discrepancies. You aren't taking apart components here. You're opening a panel and doing a broad, thorough visual sweep to spot glaring issues. Think along the lines of a leaking hydraulic line dripping directly onto a main wiring bundle. And while you're doing those visual inspections, you need to be constantly hunting for swarf. Swarf is the industry term for those sharp metal particles generated from drilling and machining operations. If the sheet metal guys leave swarf behind, the aircraft's vibration will cause those tiny little metal daggers to slowly slice right through wire insulation. Or worse, they'll bridge the gap between exposed terminals and cause a hard short. Keep your work areas clean. Ultimately, the #1 killer of EWIS that we are always looking for is abrasion. On the exam, remember that abrasion on electrical cables is specifically damage caused by chafing. It's almost always the result of a sloppy job, improper routing, missing rubber cushions on those clamps, or loose zip ties that allow the wires to just rub and chafe against the vibrating airframe, day in and day out. Your B1 test requires you to know this inside and out, and not just to pass a paper exam, but because real people's lives literally rely on your signature. So let me leave you with this final question. When you close that panel up, are you absolutely ready to sign off on a flawless system, or are you going to be the mechanic who leaves a hidden hazard behind? Study these rules, understand the why behind them, and go ace that exam. You've got this.